I'm going to start a new recording here. And what I want to do is direct your attention to the Blackboard. One moment here. One moment. Okay, so put all this stuff on. It's hard to keep it all straight. All right. So if you go into Blackboard, okay, you all see the screen here. So of course, when you go into Blackboard, you'll be brought into course orientation, right? If you go to MATLAB assignments, and there are the instructions. Click here for MATLAB, and the due date's Thursday, October 29th. Okay, that's 3 weeks from today. So you click here to see MATLAB assignments 1 and 2. And by MATLAB assignment 2, I have a partial pivoting example. So if you click on partial pivoting, this is the example, and you can download this example. The reason I'm suggesting maybe you do that is the type's a little bit small, and you could bring it on your computer and magnify it. Okay. But what I'd like to do here now is I want to talk about that example a little bit. So let me bring it up here. Oops. Hold on, not that. I don't want to share that. Let me see here. Let me bring it up. Here it is. Okay. So there are two pages to this document. And where you want to start is at the bottom of page 1. It talks about the role of interchanges. So what's going to happen is in MATLAB assignment number 2, okay, you're going to be doing LU factorization. That's a little different from what you did in your homework. In the homework, section 2.5, LU factorization only involved row operations where you multiplied a row by number and added that result to the row below. Okay, there were no row interchanges. But in regards to computation with computers, there's a note on page, it's way back in section 1.2, there's a note on page 17, a numerical note at the bottom, that says a computer program usually selects as a pivot the entry in the column having the largest absolute value. This strategy, called partial pivoting, is used because it reduces round-off errors in the calculations. And so there's a very good example here, and actually this was a student got me this example quite a while ago, so I appreciate that. And I've been using it. So here you have, this is actually from a computer science book. You have a system here. You have a system. And there is an exact answer to this. Hold on here. Okay, I don't know why I'm having kind of big font here, but the exact answer to this is going to be x1 equals 40,000 over 39,999. okay, and x2, okay, so x1, and you're welcome to write it in. It will be on the recording. I am recording this, and I'm going to post this recording where your, where your MATLAB assignment is, along with that download, along with the download document. The other answer for x2 is going to be 39,998. Okay, and that's going to be divided by 39,999. So let me put it over here. Okay, so let me cross that out. So if you were to do row operations like you do in your homework, okay, you would find that the exact answer is x1 equals 40,000 divided by 39,999, and x2 will equal 39,998 divided by 39,999. Okay, so basically x1 and x2 are almost equal to 1, 1. Okay, for the solution, almost. Now what you're used to doing is you're used to using the smallest number in a column as a pivot. So what you'd be doing is, now I want to be careful. I want to be careful how I say this. So yes, you like 1 as a pivot, but generally what you do is you use the smallest number in the column as your pivot. So if we were to say, hey, we want the computer to do that too, the computer would use the 0.000025 as its pivot. If we program the computer to use the smallest number as its pivot, okay? So let's suppose we were to do that. Let me go to the next page. What would the necessary thing be? So you would want to get a 0 where the 1 is, right? So you'd have to multiply this. Let me see here. Hold on. Hold on. You'd have to multiply this number, 0.000025, which is 25 millionths. You'd have to multiply that by negative 40,000. You have to multiply that by negative 40,000, okay, and add that to, you'd multiply the first row by negative 40,000 and add that to the second row so that you would get a 0 where that 1 is, okay, in the second equation. Now, if you do that, let me go to the next page. What happens if you do that? What happens if you do that? Well, what we're going to assume here, and I may go a few minutes over. I hope you can stay in the session, but I am recording this, so it will be there. I will make the recording available. But what we're going to do here is we're going to say, let's assume that we're using, we're rounding to the nearest 4 significant digits. Now the computer, of course, rounds much further away than that. But at some point, the computer, when it does its operations, it does round. So in this little example we're just going to say, let's suppose we're rounding to the nearest 4 significant digits. Well, what's going to happen here? What's going to happen? When you multiply negative 40,000 times the first equation, the first row, and add that result to the second row, this is going to be your resulting system. Okay, now the student actually put footnotes on the margins. Those aren't my footnotes, but you know, you can certainly welcome to read them. So here's the thing. If you added negative 40,000, like I'm focused now here on this number right here. So originally, right, I mean, you take negative 40,000 times 25 millionths, add it to the 1, and you'll get a 0 here. That's good. That's good. But when you add negative 40,000 times 1 on the first row and add it to the 1 in the second row, instead of negative 40,000, you should be getting negative 39,999. Okay, that's what you should be getting. That's what they comment on here. But if we're going to use 4 significant digits, we can't store negative 39,999. We can't store that because that's 5 significant digits. So what the computer will do is it will round it. It will round it to negative 40,000. It'll round it to negative 40,000, and that's what then gets put. That's what gets put in this spot in front of the x2 on the second equation. So if it were correct, it would, like as humans, we would put negative 39,999 there in this spot. But the computer, using 4 significant digit arithmetic, it's going to round that negative 39,999 to negative 40,000. Now let's see what the result is. When you solve for x2, okay, you're going to get a 1, which is pretty close to what x1 is if you were exact. The exact answer for x1 is 40,000 divided by 39,999. But x1, when you solve x1, you're going to get a 0. You're going to get a 0 here. Okay. Because x2 is equal to 1. 1 minus x2 then is 1 minus 1. That's 0. But the exact answer for x1 was 39. The exact answer for, hold on, I want to make sure I'm saying this right. I might have said an error here. x2 is equal to 1. And that's very close to the correct answer. The exact answer for x2 was 39,998 divided by 39,999. I may have misspoke before. But x1, when we use then x2 equals 1, and we substitute that in to solve for x1, we get a 0. Because 1 minus 1 is 0, right? So, but the exact answer for x1 is 40,000 over 39,999. So what happened is, instead of getting an answer close to 1, 1, we got an answer 0, 1. Okay, that's what we got. We got 0, 1. So we got a completely wrong answer by using the 25 millionths as a pivot, by using the smaller number in the first column as a pivot. So what we want to do is not use the smaller number with a computer. We don't want to use the smaller number as a pivot. We want to use the larger number. So what we're going to do is then we have to do an exchange step. We have to interchange rows 1 and row 2. We have to interchange them so that the bigger number in column 1 is the pivot. And that's going to be the 1. Okay, and this is what differs in section 2.5, you didn't use row interchanges. But computers are going to use row interchanges to get their LU factorizations because they want to use partial pivoting. Okay, so when you multiply the 1, okay, I mean you now want to get a 0 where this 25 millionths is. Okay, so to get a 0 there, you have to multiply the 1 by negative 0.25. You have to multiply the 1 by negative 25 millionths. Okay, and when you do that, when you multiply the first row, the first equation, by negative 25 millionths, and add that to the second row, you're going to get a 0 in this spot, which is good. And then negative 25 millionths times 1 plus 1. If you round that, you're going to get a 1. You're going to get a 1 in front of the x2. Okay, you're going to get a 1 there. Okay, so it isn't exactly right. You lost a little bit of precision, as the student pointed out here, but let's see what the result is. If you solve now this reduced system, you're going to get x2 equals 1, and then you're going to get x1 equals 1, because if x2 equals 1, 2 minus 1 over 1 equals 1. So you have an answer that's much closer to what the exact answer is. Okay, you have an answer that's much closer to what the exact answer is. And so this is why computers use partial pivoting. When they do the row reduction, they use the biggest number in the column as the pivot, not the smallest number. And you can see I mean, this is an approximation. 1, 1 is an approximation to the exact answer. You know, x1 equals 1, x2 equals 1 is an approximation to the exact answer. The exact answer was x1 equals 40,000 over 39,999, and x2 equals 39,998 over 39,999. But it is an approximation, but it's a lot better. It's a lot better than the previous. It's a lot better than the result we had before of x1 equals 0, x2 equals 1. That was just an answer that wasn't even close. Okay, so this is why computers will use partial pivoting to do the operations, to do the row operations, because it greatly reduces the round-off error. Are there any questions on that? I thank you for staying. I thank you for staying. Those who stayed, I thank you for staying. Are there any questions? And even the person that left stayed most of the time, so that's okay. So what you'll need to do is you might need to look at this, listen to this recording again. How many think they might need to listen to this again? Listen to the recording again. Okay. Oh, a lot of people. Okay. Well, that's fine, everybody. That's fine. And but at any rate, this is what's going on. And what we're going to do then on Tuesday is I'm going to show you how LU factorization in MATLAB incorporates the partial pivoting. And I thank you for staying. Thank you. And I'll stop the recording here.